We're about to dive into one of chemistry's most dramatic mysteries. Why do certain metals just blow up when they touch something as simple as water? So let's set the scene for this investigation. We've got two characters in our story, and honestly, they seem pretty harmless. Okay, so on one side, you've got this piece of metal. It's kind of dull, silvery. And get this, it's so soft you could literally cut it with a knife. And on the other side, just a bowl of water. I mean, separately, well, they're boring, right? But what happens when you introduce them? As you're about to see, the result is anything but boring. Boom. A totally fiery, violent reaction. The metal just hisses and zips across the water's surface before it bursts into flame. So what is this stuff? This is sodium, and let's call it impatient personality, is the key to this whole mystery. But here's the thing. Sodium isn't acting alone. Nope. Turns out it's part of a whole family of elements, and they all have a reputation for this kind of behavior. Let me introduce you to the alkali metals. They're all hanging out in group 1 of the periodic table. Think of this as our lineup of the usual suspects. You've got lithium, sodium, potassium, rubidium, and cesium. You could almost think of them as the super extroverts of the chemical world. Seriously, they are so reactive, so desperate to pair up with other elements that you will never, ever find them all by themselves in nature. They're always attached to something else, like the sodium in the salt on your table. All right, so we've got our suspects lined up, but what's their motive? Why are they so explosive? To figure that out, we've got to go deeper. We need to look at their atomic structure for the real clues. See, an element's personality, how it behaves, how reactive it is, it all comes down to its atomic structure. And really, it's all about how its electrons are arranged. And when it comes to the alkali metals, their entire explosive secret, well, it all boils down to one simple single number. 1. Just 1. That's it. Every single alkali metal has just one lonely electron way out there in its outermost shell. And this lone electron, it's super unstable. It's barely hanging on. The atom is just desperate to ditch it so it can get a nice, full, stable outer shell. That's like the ultimate goal for pretty much any atom. There's a sciencey term for this, of course. It's called ionization energy. And it's basically just a measure of how much oomph it takes to pull that outer electron away from the atom. And for sodium, that number is incredibly low, just 496 kilojoules per mole. What that means is it takes almost no effort at all for sodium to give away that troublesome electron. It's not just willing to do it, it's actively looking for a chance to get rid of it. Okay, so let's head back to the crime scene. We've got the motive, right? That lonely electron. But how does the crime actually go down the second that sodium hits the water? It's basically a chemical heist. The sodium atom sees the water molecule and just shoves its unwanted electron onto it. This super fast transfer, it's called a redox reaction, is so powerful it literally rips the water molecule apart. And when that happens, it releases hydrogen gas. And here's the official police report, if you will. This chemical equation shows us exactly what's happening. You have sodium plus water, and that gives you sodium hydroxide, and crucially, that hydrogen gas. That's the fuel for our fire. Right, but where does the actual fire come from? Well, this whole reaction is what chemists call highly exothermic. It just means it releases a ton of energy as heat. And there's so much heat, it's more than enough to ignite that hydrogen gas we just made. And that's what gives you the flame and the explosion. Now, you might think sodium is dramatic, but get this. It's not even the most volatile member of its own family. Oh no. There's a clear pattern here, and it gets way more extreme. So as you go down that group on the periodic table, from lithium to cesium, the atoms themselves get bigger. And that means that single outer electron gets farther and farther away from the center of the atom, the nucleus, which makes it even easier to lose. So you get this trend. Lithium kind of just fizzes a bit. Sodium, as we saw, burns. And cesium? Well, cesium just flat out explodes on contact. Yeah, the trend is crystal clear. The reactivity just skyrockets as you move down the family. To put it simply, the bigger the atom, the bigger the boom. I mean, check this out. Elements like cesium are so ridiculously reactive, they don't even need liquid water. They will react so violently that they'll explode if you drop them on a block of ice at a freezing -100 degrees Celsius. Just wild.
So there you have it. We've looked at the suspects, we've figured out the motive, we've analyzed the crime scene. I think we can officially call this case closed.
So let's just recap the key evidence one last time. It all boils down to three things, right? First, the alkali metals have that one lonely outer electron they're just dying to get rid of. Second, the reaction of giving that electron away to water releases a huge amount of heat. And third, that heat is more than enough to light up the hydrogen gas that gets created, and boom, you've got your fiery explosion.
And it's all because of that one single super impatient electron. That's what takes us from a simple piece of metal to a crazy explosion. So, now that we've cracked this case, what other secrets of the periodic table do you think we should investigate next?